All right, folks, last time we were together, we were talking about analysis of variance. We were doing a one-way study or a completely randomized design, a couple different names, and we were talking about trying to detect differences in three or more means. We call them treatment means now. Sometimes we reach the conclusion at least two means differ, and it's the first time when we make a conclusion that we're not done. Because if you tell me at least two means differ, the next logical question is, well, which means are they? So I'll take a look at the example we were working on. We were going through the diamond data set, and we were looking at the size of the diamonds based on the clarity level. And there are five clarity levels: IF, VS1, VS2, VVS1, and VVS2. Because there's only one factor level in this particular example, the treatments are the various factor levels, and our goal is to compute them. So you can see the null hypothesis here at the bottom of the screen. We're saying in the null hypothesis that the mean caret sizes are the same for all five clarity levels, and the alternative says nuh-uh. And nuh-uh is a good way of thinking about that alternative because it's saying at least two means. It's not specifying. Sometimes people say at least one mean differs. Well, if at least one mean differs, then at least two means differ. You can say it either way. That's fine. And you know, the last time we were together, we looked at a printout, and there's a variety of printouts we could choose. They all give us the same information. Basically, this is the Excel printout, and there's between group variation and within group variation, and ultimately we get over here to a test statistic and a p-value. Now, if we're using the p-value to make a conclusion, that's all we need. If we're using the old-time rejection region, don't do it, then the critical value would be helpful. So it's the p-value here. That's what we're looking at. And so what we saw last time is that when we're testing at any alpha, we'll use an alpha equal 0.10, we reject. Sufficient evidence to indicate that the mean caret weight for the five clarity levels differs. At least two means differ. The assumptions we talk about: random and independent samples of diamonds, distribution of caret weights, the distribution of your response variable for the five clarity levels are all approximately normal. So you have your normal assumption. And then we have your equal variances. The variation of the response variable, the caret weights for the five clarity levels, are all equal. And so that's where we ended up. So the question is, what's next? And what's next is called a multiple comparison of means. Now, what we know, what we looked at in the past, not too long ago actually, is we looked at how we can compare two means, so-called mu1 and mu2. We created a confidence interval. We also did a test, but here we're talking about confidence intervals for the difference between two means. And we ended up with two numbers, right? We ended up with a positive endpoint and a negative endpoint. Well, now the challenge that we're going to run into is there's not just one pair. It's not just two means. It's, in this case, we have five means. And so now we have to consider how many pairs do we have? And if there are five means, the way that you can do this real quickly is take the number of means that you have, number of levels, number of treatments, take that number times 1 minus that number, 5 times 4, and then divide by 2. So 20 divided by 2, there's 10, and I've just listed them here. IF, VS1, IF, VS2, you can see all of them. There are 10 treatment means that we want to, I shouldn't say 10 treatment means. There's 5 treatment means we want to compare, which results in 10 different comparisons. So here's where we run into trouble. If we create 10 confidence intervals using a 95% confidence level, or a confidence interval, each time we do a comparison, our error is going to be 5%, right? 95%. Every time you do a confidence interval, there's a 5% error. Well, that's the comparison-wise error, but we have 10 of them. And so the experiment-wise error could be as high as 50%, which is way too high. Now, there's some research that's been done that says there may be a little bit of an overlap, but it's really hard to figure out what that overlap may be between these errors. And so ultimately what we end up saying is, let's just bound it. Let's give it an upper bound, 50%. That means when we do these 10 intervals using 95% confidence levels, our overall reliability is only, our overall error rate would be 50%, so our overall reliability would be 50%, and that's way too low. So the overall error is too high, the overall confidence is too low. And so this dude, Bonferroni, he said, duh, and I don't know if duh is a term. It's probably going to come back in style at some point. But duh was a big thing when I was young. And if you were with somebody and they said something that was extremely obvious, you might call them Captain Obvious now, but we would just look at him and be like, duh. It's like, it's such a no-brainer. If you want 95% overall reliability for 10 comparisons, there's a duh here. The duh is, take that overall reliability you want, think about it in terms of the error, use an alpha of not 0.05 for each comparison, but divide that by the number of comparisons. Use 0.005 for each comparison. So do 10 different intervals, but use 99.5% reliability for each of the individual intervals, and that way when you have 10 of them, you get the overall reliability you want. And I think I can hear you echoing through my earphones right now, or earbuds, if I was cooler and hipper and younger. You would be saying, duh, that makes sense. And that's why I look at the Bonferroni. There's several different multiple comparison procedures. There's a Tukey, there's an LSD. Well, that one's kind of groovy. At least significant difference. I don't know what you think LSD is. There's a Chaffee, there's a Sadak, there's all sorts of different types. But the Bonferroni is the one that's easiest to understand. That's why it's the one that I cover in class. It's also the easiest one to do if you're using, oh, I don't know, say Excel, which I'll talk a little bit more about in a second. So once we get those intervals, we're not going to use 0.05. We're going to use this new improved, and actually it's the alpha divided by the number of comparisons. That's what we're going to use here. We're going to get confidence intervals, and depending what textbook we're using, it might be chapter 7, it might be chapter 8. My pen may go a little crazy on us here, but we interpret them the same way we've seen before. When we do a comparison, if we compare mu1 and mu2, or mu IF and mu VS1, when we look at the endpoints, if you have two positive endpoints, that's going to indicate the first mean's bigger than the second mean. If you have two negative endpoints, that's going to mean the first mean is less than the second mean. If you have a negative and a positive, that's where the difference between the means might be 0, and we've talked about this before. That's when we're going to say we can't determine which mean is bigger. Now, here's where I struggle. You know how I feel about Excel. By this point in the semester, everybody knows how I feel about Excel. I have a love-hate relationship with Excel. I usually hate it, but occasionally I love it, depending on what we're doing in statistics. It's a great software package. I love it, love it, love it as far as statistical analysis. Meh. So here's why I dislike Excel in this particular case. Once you do the analysis of variance, and we've seen how easy it is to get the analysis of variance printout. There's a nice little feature. You go to the data analysis tool pack. You do the one-way analysis of variance, and you can do it. So you get the test statistic, you make your conclusion, something, at least two means differ. But then going to find the differences, it leaves you kind of hanging. There's nothing really out there for you within Excel. And so what you need to do in that case is take each of the comparisons you want to look at and go back and do one of these. Create a confidence interval for the difference between two means. And that's not easy to do in Excel. That requires a template. That requires some functions. That requires a fair amount of work. So what I'm going to do is I'm going to show you, I'm going to cheat a little bit. And I don't really consider this cheating because most of the software packages that work with statistics as a subject will give us this. The one I used to use was called Statistics with an X. Clever, right? Here's how the results are presented in that particular software. And a lot of the software programs do something very, very similar. And so what this printout will show us is the overall experiment-wise alpha that was used. So there are 10 comparisons being conducted on this particular printout. You can't see it necessarily yet, but I'll hope to explain it. So each of the comparisons, each of the individual comparisons is taking place at 0.05 divided by 5. So what the software has done for us is it's gone ahead and compared VS2 to VVS2 and VS2 to VS1 and VS2 to VVS1. Whoops, my pen goes crazy when I try to film and do this. And then it's going to do this one. And I'm trying to pair up, and yeah, it's going nuts. Sorry about this. So I'm trying to link all the different comparisons that are being done. There we go. I think there's 10 comparisons there. Good luck seeing that. But every combination of two of these 5 is being done. And here's what's happening. When VS2 was compared to VVS2, here's what I know. When VS2 was compared to VVS2, the interval ended up being a negative and a positive. Now you don't see that. Those results aren't shown anywhere. But the fact that you have these two letters here, these two A's, oh my God, this cursor's driving me crazy right now. Let me get my eraser. Let's just get rid of this. I should be able to erase it. Here we go. The fact that you see, let me get my pen. The fact that you see this A and that A, that meant when you compared the VS2 to the VVS2, it was a negative positive. That's why they're grouped together. In fact, all 4 of these treatments, VS2, VVS2, VS1, VVS1, when you compared any 2 of them, There was a negative and a positive, meaning we didn't detect differences between the mean carat weights of any of those clarity levels. There were no differences found. It's only when the IF was compared to the VVS1. That's where you saw, and the way that statistics, because I have a lot of experience with this particular software package, it always considers when it does a comparison, when it does the first mean minus the second mean, it'll look at the clarity level and it looks at the letters of the clarity level. And because IF begins with an I and all the others begin with the letter V, IF is considered the first group and the VVS1 is considered a second group. IF is the first group, VS1 is the second group. And in each of those cases, what we're going to end up with is a negative negative. So when IF was compared to the VS2, we got a negative negative. When IF was compared to the VVS2, it was a negative negative. When IF was compared to the VS1, was compared to the VVS1, they were all negative negative. That's why this letter here and also this column, I'm highlighting this, the letter B here, I'm trying to highlight the letter B, it sets it apart. It's saying that the IF is different than all the others. There's really no difference. We can't detect a difference. And you can see the sample means here in this column. There's slight differences in the sample means, but they're not big enough differences within the sample means to detect that the population means differ. Whereas the IF mean here is a lot different. There's a big enough difference between the IF sample mean and the other sample means where we're going to make the conclusion that the IF group has a lower mean than all the other groups. You see I separated these with commas because I can't tell a difference in any of the population mean carat sizes of those four groups. They're all grouped together and they're connected in this case by the letter A. And that's how statistics reports as a result. Excel is going to make you do each of the 10 intervals. And when you did that, you would find 6 of the intervals, the 6 that when you compare any of these four, those 6 intervals that you create when you're looking at mu VS1 minus mu VS2 or mu VVS1 minus mu VVS2, all of those are going to be negative positive. I can't detect differences, can't detect differences, can't detect differences. That's how they're grouped. It's a really nice summary of the results. Now, let me show you another example. Let's say we want to help treat children that are suffering from an upper respiratory tract infection. That sounds like a pretty good thing to do. The 3 treatment groups considered were labeled as DM, honey, and a control group where no treatment was administered. So parents are giving their kids cough syrup. One of them is called DM, one of them is just honey, and one of them is just control group, which is just a placebo. The response variable is measured as severity of the children's coughing symptoms. The higher the value, the more severe the symptoms. That's what we're told here. It was desired to determine if the mean severity differed for the 3 treatments. So the response variable is the coughing, the coughing symptoms, the severity level of the cough. And I don't know how we're quantifying that as some kind of numerical measure. I think we're asking the parents, rate your child's cough. Is it severe? Is it not severe on a 10-point scale, on a 100-point scale? The factor is the type of treatment that was administered. Why is my cursor doing this? There we go. The treatment. There's 3 levels of treatment, DM, honey, and control. And because there's only one factor, the treatment levels are the various treatments, the various levels of the factor. So DM is a treatment, honey is a treatment, control is a treatment. Our goal is to compare them. Null is going to say there's no difference between the mean cough severity, severity level of cough for the 3 treatment levels. The alternative is going to say, yeah, there is. At least 2 means differ. And so we go and we do our thing. Now, I didn't show you the Excel printout, but the Excel printout would look exactly like the statistics printout. You can see pretty much the same things are there. Let me kind of go back. Let's see if I can go back. That's the best way of doing this. Where is it? This is taking longer than I'd hoped. Sorry about that. There we go. You got sums of squares, degrees of freedom, mean square, F, and p-value. Now let's go back forward. The next page. There we go. Sums of squares, degrees of freedom, mean square, F, p-value. The Excel has a critical value for the F, but we don't use it. We're going to use the test statistic. Well, the test statistic is 17.51. The p-value is 0.0000. Really, any alpha you choose, you're going to reject H naught here. At alpha equal 0.01, we reject. P is low. We reject the O. There's sufficient evidence to indicate that mean severity level for the 5 treatments. You should have the word mean on here. It's off the screen. I'll type it in with my mouse. The mean severity level for the 5 treatments differs. The assumptions: you need random and independent, you need approximately normal, you need equal variances. So random and independent samples of children in each groups. The distribution of the severity levels, that's the dependent variable, that's the response variable for the 3 treatments, are all approximately normal, and the variation of the severity levels are all equal as well. So you have equal population variances from normal populations. Random and independent samples. All right, so we're saying there at least 2 means differ. Now let's go find them. We've included at least 2 of the top of the 3 treatment means differ. Now we conduct the Bonferroni follow-up analysis. Remember and it's what's interesting. I've always thought this about this problem, and I've never been able to find the data. I think we were told in the problem that higher numbers indicate more severe. Let's see if I see that right. The higher the value, the more severe the symptoms. I think that's backwards, actually. But all I want you to do is, and when I say that, the control group, where there actually is no treatment, has the lowest sample mean. The DM, the honey, I think that's backwards. I would think that the honey and the DM, the actual treatments themselves, would probably be effective, but who knows? All I want you to do is take a look at the results and be able to summarize for me what your conclusions are. Again, Excel is going to have you go and create, let's see, there's going to be, and see if I can do it without my cursor freaking out. There's going to be 3 pairs to compare here. Much like what you guys are going to do for me with your data this semester. You have 3 models of vehicle, or you have 3 levels, locations of homes or apartments. So you're going to have 3 treatment means. So you can compare 1 and 2, 1 and 3, 2 and 3. In this case, I can compare control with DM, control with honey, DM with honey. Again, when statistics compares control with DM, because C, so let me do the 3 comparisons. Let's see if I can do it here. C minus D, C minus H, and I'm just doing them alphabetically, and D minus H. Those are the 3 comparisons that you would have to come up with in Excel. So it'd be 3 separate analyses. When we do that, the interval, this is going to be negative, negative, and I know that because C is less than D, and these things are not grouped together. If it was negative, positive, these 2 would be grouped together, but because they're not, I know there's a difference. C minus H is also going to be, actually all these are going to be negative, negative because of the order. This is the way your intervals would show up. The fact that they're all negative, negative means they're all going to be, we're going to say they're all significantly different. And we know the direction. We know that the control group has the lowest mean. So that's going to be less than the DM group, which is going to be less than the honey group. And I can write it either way. I can put honey's greater than DM, which is greater than control, or I can put control is less than DM, which is less than honey. All right, summarize. We are doing a test. We're just doing a test hypothesis to determine if the treatment means are all equal or not. If we reject H naught, if we say there's sufficient evidence to indicate at least 2 treatment means differ, then we got to figure out where the differences are, and that's confidence intervals. So we start with the test. If you reject, you follow it up with confidence intervals. If you fail to reject, if there's insufficient evidence to indicate at least 2 treatment means differ, now what you're going to have to do is stop. There's really no more to do. Now, sometimes in your homeworks, I'll make you go and follow it up and do some more work and do the multiple comparisons, even if you fail to reject. But typically when you fail to reject, you're done. You stop. And I know a lot of times when I say that, you stop. Ooh, students are smiling. They're like, yes, we get to stop. That's not what we want. When we're doing analyses, when we're trying to analyze data, we want to find differences between the means. That's our goal. We're hoping that we can detect differences so that we can come up with a way of helping our kids and their coughs. Trying to find out some relationship between carrot size and clarity level, or price and clarity level. So this is the one-way analysis of variance follow-up work. The one I'm going to make you comfortable with or work with is the Bonferroni. But as I mentioned, there's others out there. The Tukey is probably the most popular, Tukey. It controls the experiment-wise error, which is the error that we really need to keep an eye on. The only reason I go with Bonferroni is, and I've gone with Bonferroni for years and years and years because it's the easiest one to understand. But now that we're using Excel, it's almost a must, because all Bonferroni makes us do is take our overall error for the alpha that we're looking for and split it into the number of comparisons. So in this particular case, let me just go here. It's taken an alpha 0.05 And the three comparisons, it's going to split it three ways. So when I have a calculator handy, when I take 0.05 and divide it by 3, I get 0.016666666666. When you're doing it in Excel, I would probably use an overall alpha of 0.06 because splitting that three ways will give you a 0.02, which is a little bit easier to work with. So then you're getting 98% confidence intervals, and that's a little bit easier number to work with. But I'll show you how to do all that at another time. So that is the one-way analysis of variance. So long.